more than one time. So if we're interested in seeing whether it approaches from above or below ultimately, what we can do, okay, looking at this, I can figure that 10 is larger than any of the zeros of either polynomial here. 10 is a larger number than either of the zeros. So we have 2x squared. 10 squared is 100, so we have 200. 3 times x. X is 10, so that's minus 30, plus 1 divided by 3 times x squared is 300. 300 minus 2. Well, this top is 200 minus 29. So that's going to be less than 200. Down here you have 300 minus 2. So just by looking at this, I'm not going to go through all the calculations, but just by looking at this, this value is less than 2/3. So the scenario where I said it approaches from the bottom and goes asymptotically close to the line y equals 2/3, that's the model that's correct for this function. So with polynomials, you investigate their behavior by dividing everything through by the largest power of x. Lots of other functions out there become more and more difficult to investigate, and you have to use reason. You have to use sometimes difficult techniques. L'Hopital's rule will help you often. But here's another one, exponential functions. Now this number here is called e. It's a very mathematically important number. It's an irrational number, and so it doesn't repeat. Its decimal formulation never repeats, and it never terminates. Well, I'm going to use a perhaps color that might show up a little better. No, that doesn't work. Let's try green. All right, green works. Yeah, green works. All right, now e is called the base of the natural logarithm. That's not important right now. E is a number that shows up all the time in all sorts of natural functions. There are many ways for defining the value of e, many mathematically equivalent ways of defining the value of e. But essentially, e is an irrational number. It's approximately equal to 2.7828. And it goes on and on and on forever. But that's approximately the value of e. All right. It's another number like pi. It's mathematically and physically important, but it never terminates and it never repeats. So it's a non-repeating, non-terminating decimal, or in other words, an irrational number. Now, why is e important? Well, a lot of functions show up of the form e to the x. So in other words, e is being taken to the power of x. Now, e is a number greater than 1. There's two different behaviors for taking an exponential of a number. 1/2 to the x gets smaller and smaller and smaller as x gets bigger. As x approaches 0, this goes to 1. So, 1/2 to the 1/2 power is larger than 1/2. 1/2 to the 1/4 power is larger than that. And as that exponent approaches 0, this function here in total approaches 1. The other behavior is for numbers greater than 1, and they approach 1 as x goes to 0, just like these do, except when x is greater than 0, they get bigger and bigger and bigger. Now, when x is a negative number, these types of values which are which are greater than 1, they get less than 1. Because remember, 2 to the minus 1 power is 1 over 2, which is less than 1. Any number to a minus power, a to the minus n equals 1 over a to the n. So if a is greater than 1, a to the minus n, if n is a positive number, is going to be less than 1. All right. If a is a number which is less than 1, then a to the minus n is going to be greater than 1. So these are the two types of behaviors. There is a third class, and there are two numbers that fit this, 1 and 0. 0 to the x and 1 to the x never change. It doesn't matter what you plug in. You can multiply 0 by itself 500,000 times and you're still going to get 0. You can multiply 1 times itself any number of times and you're still going to get 1. There are a couple others, like the imaginary constant or -1. They change, but they change in a somewhat predictable manner. And when you take negative numbers to non-integer powers, that's going to be getting into something that's way in the future. Right now we're talking about positive real numbers taken to real number powers. So e to the x is an important e to the x. In general, it takes the form of some constant a times e to the kx, where k is another constant. And these two constants will depend on some sort of physical constraints, some sort of physics or chemistry or whatever the subject you're dealing with. Population, possibly, if you have an exponentially growing population. A very common example is the nuclear decay of elements, of radioactive elements such as uranium. Now what that says is that the amount that you have after a time t is equal to n0, which is the amount that you started with, times e to the minus kt. Notice that's a minus. What that means is as t gets larger, it asymptotically approaches 0. Now, radioactive materials have a characteristic called a half-life. And K is a constant which is dependent upon the particular half-life of the material. The half-life of the material is, for all intents and purposes, an intrinsic quantity. It has to do with the physics of the nucleus. It can be hard to calculate, sometimes impossible to calculate, and you just have to get the value experimentally. But essentially, K is a positive number which depends upon the half-life. And the half-life can be determined experimentally. And what you have here is you start off, when t is equal to 0, e to the 0, anything to the 0 power other than 0, that's a weird behavior. Anything other than 0 taken to the 0 power is 1. So this quantity here is 1 when t is 0, so 1 times n0 is n0. So at time t equals 0, you start off with some amount n0. And then as time goes on, it just goes down like this. Never quite touching 0, but it gets arbitrarily close. As time goes on, you get closer and closer and closer to 0 in this manner. This is a common natural growth. Now, another one is if you assume, say, that you have bacteria in a petri dish, and you start with one bacterium, and you assume that they have, for all intents and purposes, an infinite amount of resources available, an infinite amount of food and space, well, and that none of them die. So you're oversimplifying it. But the simplest population growth model, and you can do this